Hello, my precious friends. I really hope that you are doing great. Welcome to our today's class. It is our 8th lesson on the 7th topic of Form 3 work, which is called Electrostatics 2. As usual, let me commence by giving the quote of the day, which states that growth comes from a series of mistakes. We shall discuss that quote at the end of our class today. So today we are looking at the energy stored in a charged capacitor, and we are saying that a capacitor usually stores energy which is equivalent to the work done W against the repulsive and attractive forces, that is when an electron is being added or removed from a charged plate. Remember, charging of the plate simply involves transfer of electrons from the negative terminal of the battery to the plate of the capacitor. So this energy can be converted either to heat, light, or other forms of energy. Then, from the equation of capacitance, we did say that capacitance is simply charge per unit voltage, So we said that capacitance can be given by Q over V, whereby we also said that from the same equation, then the charge Q can be given by the product of capacitance and the potential difference. That is, charge Q is equals to CV. So if I hold capacitance constant, if I take C to be my constant in this particular equation, it simply means that the quantity of charge on the plates of a capacitor will always be directly proportional to the potential difference. So PD or Q will always be directly proportional to V, that is if we hold capacitance constant. So from this equation, charge Q will be directly proportional to potential difference V. Then we know that since the charge stored Q, that is the charge stored in the plates of the capacitor, is directly proportional to the potential difference applied V, that is the potential difference across the source, then it follows that a graph of V against Q will always be a straight line graph. Remember, we said that the capacitors, the plates of the capacitor usually charge until the potential difference across the plates of the capacitor is equal to the potential difference across the battery or the potential difference across the source. So that simply means that if the source or if the battery has a larger potential difference, then the plates of the capacitor will also acquire a lot of charge. Therefore, the charge will always be directly proportional to the potential difference of the battery. Therefore, the larger the potential difference, the more the charge that will be acquired on the plates of the capacitor. And of course, the smaller the potential difference across the source, the smaller the amount of charge that will be attracted to the plates of the charging capacitor. So charge Q is directly proportional to potential difference V. Then it follows that if two quantities are directly proportional to each other, it simply means that their graph will be a straight line graph, such as this one, which is shown here. So since the charge stored Q is directly proportional to the potential difference V, it follows that a graph of potential difference V against charge Q will always be a straight line graph. And in this case, our graph is starting from the origin, that is 0, 0. That is showing simply that the charge and the potential difference across the battery or across the source are actually directly proportional to each other, such that when one of the quantities is increasing, the other quantity also increases, and of course vice versa. So if we find the area under this particular graph, so remember our graph is this particular straight line. So when we talk of the area under the graph, we are simply talking of the area between our line OA and actually this particular horizontal axis, that is the Q axis. So the area between our graph and this horizontal charge Q will be the area under that particular graph. So this area, which is actually shaded, that is area OAB, that is the area under the graph. So the area under the graph, you can clearly see that area OAB is in triangular shape. Therefore, when you talk of the area under the graph, will just be equal to the area of triangle, the triangle OAB. Then we know that the area of a right angle triangle is given by a half base times height. In this case, our base is of course Q, that is OB, and you can see that OB, we are moving along the Q axis, which is the horizontal axis. So the area of the triangle is a half base times height. So our base is Q, so that is the distance from O to B, which is a movement along Q. So the base is actually Q. Then the height, of course, is the distance from B towards A, or the distance from A to B. That is the distance along the vertical axis. And you can see as you move from B to A, you're actually moving along the voltage axis. Therefore, our height is actually V. So our height is V. So area is a half base times height. So a half of the base is Q, then the height, of course, is a potential difference V. But from current electricity 2, in our very first lesson of current electricity 2, you can just refer in this particular lesson. From our first lesson under current electricity 2, we did say that the charge, that is the product of Q and V, will always give you the work done in moving a charge Q, that is through a potential difference V, which is in volts. So we said that from current electricity 2, lesson 1, that the charge, that is the charge or the work done in moving a charge Q through a potential difference V, is given by the product of Q and V. Then we say that Q and V will always give you the work done in moving that particular charge. So this is also the energy which is stored in that particular charged capacitor, that is that particular work done. So from this formula, we can clearly see that a half of Q simply means that we are finding the average of Q. Then, so it means that the area under the graph will be equal to the work done, which is equals to the average of the charge Q multiplied by the potential difference V. Therefore, the work done W will be equal to the average charge. So Q divided by 2, that is what we mean by the average charge, then multiplied by the potential difference, which is actually V. So the work done W will be equal to a half of Q, that is this particular formula here, a half of Q times V. So a half of Q simply means the average charge, because average simply means we are simply taking the charge divided by 2. So the work done W is equals to average charge, that is a half Q, multiplied by the potential difference V. And clearly we can see here that a half of Q times V is equals to the area under VQ graph, because this particular area was equals to the area of a right-angled triangle which has the 90 degrees at point B. So a half of QV, which is equals to work done, is equals to the area under potential difference V against charge Q graph. Now the work done, the equation for the work done can also be expressed in other formats. For example, 1, remember we said that Q is equals to CV, so I want to substitute this particular value of Q with CV. Therefore, the work done can also be given by a half of, where I have Q, I want to substitute with CV, so this will be a half of Q will be CV, then multiplied by V. So of course, V times V will get V squared, so this equation will become a half of C times V squared. So this is also another equation that we can use to find the work done in moving a charge. Also, we can also express the same equation in terms of Q and C alone. So that simply means that we will substitute the value of V. Then of course, we know from this particular formula, if Q is equals to CV, then V can be given by Q divided by C. Or also from this particular equation here, V can be given by Q over C. That is, if we make V subject of the formula in this particular equation. So because V is equals to Q over C, I want to substitute it in the place where I have V here, so that this equation will become a half of C times V, but my V is Q over C. So this will be a half of C into Q over C. Remember, Q over C is just representing our V. But because the V was squared, it means we'll also square Q and we also square C. So this equation will become a half of C multiplied by Q squared divided by C squared. That is, I've just opened this bracket because this one simply means that each and every term within that bracket must be squared. So this will be half of C multiplied by Q squared over C squared. Then of course, C goes into C squared C times. So this will simply be, we shall remain with only one C down here, so that we have 2 multiplied by C, which will give us 2C. Then of course, on the numerator, we are remaining with Q squared. So this will be Q squared divided by 2C. So the work done can also be given by Q squared over 2C. So these are the different formats or the different formulas that we can use to compute the work done in moving a charge from one point to another. Then also from our graph, that is a graph of V against Q, the graph of V against Q gives the reciprocal of capacitance. So we can clearly see from this particular formula, if Q is equals to CV, then here we are plotting a graph of V against Q, meaning that V is on the y-axis, then Q is on the x or the horizontal axis. And because our graph is a straight line graph, we have to compare its equation with the equation of a straight line graph that you learned in mathematics. Of course, from math, you did say that y, equation of a straight line graph, will always be y is equals to mx plus c. Of course, where m is the gradient and c is the that is, c is the vertical intercept or the y-intercept. So in this case, I want to play around with q is equals to cv such that it comes to this format. So I'll simply make v subject of the formula. So this one, I'll just divide both sides by c so that I have v being equal to q over c. So v can also be written as q over c is just the same as saying 1 over c multiplied by q. Because if you take 1 times q, you'll just get q over c. So this equation can be expressed as v is equals to, that is, if we make v subject of the formula, we shall just get v is equals to 1 over c multiplied by q. So I'm separating this way because I have my v on the y-axis. So I want it to rhyme with the equation of a straight line graph, which was y is equals to mx plus c. That is from mathematics. So you can see now v is rhyming with my y, and you can also see that v was on the y or the vertical axis. Therefore, v is rhyming with my y. Then you can clearly see that the reciprocal of c is equals to the gradient, which is m. Therefore, the gradient of a voltage against charge graph will always give you the reciprocal of capacitance. Therefore, the gradient of VQ graph will always give you the reciprocal of the capacitance, as you can clearly see here. M is rhyming with the reciprocal of capacitance, which is actually 1 over C is M. And from mathematics, we did say that M will always represent the gradient of that particular graph. Therefore, the gradient of a VQ graph will always give you the reciprocal of the capacitance. Yeah, you can be given maybe a sample graph with some values, then someone will ask you maybe to compute the capacitance of those particular capacitor that was used in that experiment. So you simply find the gradient of the graph that you are given, if you are given a graph of V against Q. Then after finding that gradient, you simply equate it to the reciprocal of the capacitance. Then of course you compute your capacitance. So if suppose we were plotting a graph of Q against V, if we were to plot a graph of Q against V, then in that case, the capacitance will be equal to the gradient of the graph. If you just say y is equals mx plus c, so that means if you have a graph of Q against V, then the capacitance will be equal to the gradient of that particular graph. But if you have a graph of V against Q, then the capacitance will be equal to the reciprocal, or the reciprocal of the gradient, or simply the gradient will be equal to the reciprocal of capacitance. Next, we look at some examples involving computing the energy stored. So we are told that a 2 microfarad capacitor is charged to a potential difference of 120 volts. So we are required to find the energy stored in it. So here we are given the capacitance C, we are also given the potential difference V. So we simply look for the equation of the energy stored, which involves, of course, the capacitance C and the voltage V. So we know that the energy stored is just the same as saying the work done in moving that particular charge from one point to another. Therefore, we said that the work done from our previous slide, we have just said that the work done will be given by a half of Q multiplied by V. That is the product of the average charge multiplied by the potential difference V. But because we are given the charge Q, that is, we are given the capacitance C and the potential difference V, we shall look for a way of eliminating Q because we don't have Q in this particular case. Then we know that Q is equals to CV, so I'll simply substitute. Where I have Q, I'll substitute with C and V, so that this equation becomes work done is equals to a half of CV, then multiplied by V. Of course, V times V, I'll just get V squared. Therefore, work done can be given by a half multiplied by C of, then multiplied by V squared. So this will be equal to a half of C. The capacitance I'm given as 2 microfarad, but we know that the SI unit for capacitance is actually the farad. Then we know that 10 power 6 microfarad is equals to 1 farad. So what about 2 microfarad? So to convert the 2 microfarad into farad, we'll just multiply times 10 power negative 6. That is to convert it into the SI unit, which are simply the farad. Then of course times V squared, we are given the potential difference as 120. So times 120 squared. So if you compute that, you will simply get 0.0144 joules. So that is our energy that was stored in that particular capacitor. Then question 2, we are told that a 20 microfarad capacitor is charged to 60 and isolated. Isolated simply means that it does not lose the charges, or it does not interact with external, that is conductors, which could cause leakage of charge. Then it is later connected across an uncharged 100 microfarad capacitor. So if the 100 microfarad capacitor is uncharged, it simply means that the charge on it is actually 0. Then we are told to calculate the final potential difference across the combination. So to find the final potential difference, we just need the equation of charge, which was Q is equals to CV. So to find V total, or the final potential difference, we need to have the total capacitance. We also need to have the total charge. So let's start by finding the charge through the 20 microfarad capacitor. So the charge through the 20 microfarad capacitor, of course, is equals to CV. So the capacitance through the 20 microfarad capacitor times the voltage, or the potential difference across the 20 microfarad capacitor. So we are told that the 20 microfarad capacitor, of course, its capacitance is 20 microfarad. Of course, to convert it into SI units or into farad, we just multiply times 10 power negative 6. That is to convert the microfarad into the farad. Then the voltage, or the potential difference across the 20 microfarad, we are told that it was charged to 60 volts. So 20 times 10 power negative 6, of course, 2 times 6 will just get 12. Then 2 zeros will simply move the decimal, so that we have 20 times 10 power negative 6 times 60 will simply get 1.2 times 10 power negative 3 coulombs. So this is actually, I've just expressed it in standard form. So once we have the charge through the 20, we can now find the total charge, because remember, the only thing we need is the total charge and the total capacitance, because once we have those two, we will easily compute the total potential difference, or the final potential difference across that particular combination. So therefore, Q total will be equal to the charge through the 20 microfarad plus the charge through the 100 microfarad. Again, remember, we are still using these tables for the parallel arrangement. We say that for any parallel arrangement of capacitors, Q total charge will be equal to Q1 plus Q2 plus Q3. So that is why I'm adding the charge in this particular case. So to find Q total, because we only have two capacitors, so it will just be the charge through the 20 microfarad capacitor plus the charge through the second capacitor, which is the 100 microfarad capacitor. So charge through 20 microfarad capacitor, we have already computed as 1.2 times 10 power negative 3. Then of course the charge through 100 microfarad capacitor is 0. So it is 0 because we are told from the question that it is later connected across an uncharged 100 microfarad capacitor. So because it is uncharged, it means the charge through the 100 microfarad capacitor is actually 0, because it does not contain any charge. Then of course 1.2 times 10 power negative 3, that is coulombs plus 0 coulombs, you will simply get 1.2 times 10 power negative 3 coulomb. So now we have the total charge, so our task is to find the total capacitance. So the total capacitance, because we are told that it is connected across. Remember, connecting across simply means that they are being connected in parallel. But when they are connected along, then we say they are being connected in series. So connecting across simply means that they are being connected in parallel. Then we said that for any parallel arrangement, if you want to find the total capacitance, you simply sum, or you simply add the capacitances of the individual capacitors. So because in this case we only have two capacitors, that is the 20 microfarad capacitor and the 100 microfarad capacitor, it simply means that C total will be equal to the capacitance of the through the 20 microfarad capacitor plus the capacitance of the 100 microfarad capacitor. So of course, which is equals to 20 microfarad plus 100 microfarad, which will just give us 120 microfarad. Then we know that the SI unit for capacitance is simply the farad. Then we know that 10 power 6 microfarad is equals to 1 farad. So what about 120 microfarad? So of course, to convert into farad, you just multiply times 10 power negative 6. So that is to convert 120 microfarad into farad. So 120 times 10 power negative 6 farad. Then of course I'll move the decimals in between 1.2 so that to convert it into standard form, which will simply give us 1.2 times 10 power negative 4 farad. Now once we have the total capacitance and the total charge, we can easily compute the total potential difference, or the potential difference across the combination. So again, we know that Q total is equals to C total times V total. So if you want the total potential difference, which is V total, we simply make V total subject of the formula, that is by dividing both sides by C total or the total capacitance. So V total will simply be equal to the total charge, which is Q, divided by the total capacitance. So the total charge through the combination, we have already computed it as 1.2 times 10 power negative 3 coulomb, then divided by, so 1.2 times 10 power negative 3 coulomb divided by the total capacitance, of course, is 1.2 times 10 power negative 2, that is negative 4 farad. So 1.2 times 10 power negative 3 divided by 1.2 times 10 power negative 4 farad. So this will simply give us, of course, 1.2 divided by 1.2, you'll just get 1 because they will cancel out. Then 10 power negative 3 divided by 10 power negative 4, we shall simply use the laws of indices. That whenever a power is negative, then when it is on the denominator, if it moves to the numerator, then the power must be negated. So if it is negative, if we move this one to the numerator, the power will become a positive, courtesy of the laws of indices, actually, which are taught in Form 2 mathematics. So this will be equal to 1.2 divided by 1.2, we'll just get 1. Then 10 power negative 3 was already on the numerator. Then 10 power negative 4, if I take it on the numerator, the power will now, I'll just multiply the power by a negative. Of course, negative times negative 4, you just get a positive 4. Then from here, because the bases are the same here, that is base 10 and base 10, so this one simply means that whenever you multiply, you can add the powers. So this will be 1 multiplied by 10 power negative 3 plus 4, of course, which will give us positive 1. So that will be 1 times 10 power 1. Of course, 10 power 1 is just 1. Then, 10 power 1 is just 10. Then 10 times 1, you'll actually get 10 volts. So that is how to behave when you get questions of that particular manner. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that growth comes from a series of mistakes. So the quote is encouraging us not to be afraid of making mistakes in life. This is because mistakes usually help us to learn important lessons about life. So the quote is also encouraging us to be risk takers, because nothing good comes from comfort zones. Yeah, if you don't take risks in life, then expect nothing good, because all good things involve struggling, involves effort, involves hard work, and of course they are not found in comfort zones. And lastly, recall that it is okay to try and fail, because he who has never made a mistake has learned nothing about life. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you're new to the channel, kindly hit the subscription button and turn on the notification bell so that whenever I upload a new video, you'll get notified. Thank you for the continued support. I really appreciate. If you know any student that you wanted to think would benefit from this content, kindly share to them my link or share my content or my channel to them. Until next time, this is Kind Tuition Academy.